Can you hear me? Good. Hello, everyone. I'm Xian, long time no see. Today we're gonna talk about a tool called Address Sanitizer. This is a tool that allows you to detect memory errors in a very convenient way. Today we're gonna understand what memory errors are. We will talk about the overflow, buffer overflow for the stack and the heap, and we will also talk about the use after free, and also double free and memory leak, and the address sanitizer help you to detect those kinds of errors. I think when you do the, for example, if you were doing the assignment 3 in the EE209, you might see this kind of error message a lot. For example, if you type the client 1 minus P2000, if you are taking EE209, you know what does it mean. It creates a large number of the users and try to do something and try to unregister those. And if you give a very large number, then it may cause some problem because depending on your logic, it may have some logic error, memory error in the expansion part, or your register customer by itself has some error, and it caused a segmentation fault. And one way you might try to debug this kind of memory error is using GDB. What you can do is that run the program with the GDB and run it with the argument, and it will show you that where this program crashed. In here, it says it crashed at the string compare, and it caused some error when it does the string compare. You can see this string compare SSE2 unaligned is an optimized version of string compare. Just for your information, string compare is a very common function, library function that we are using a lot. And if we are working with a very large size of string, then this can cause some performance degradation. So to avoid that, because this is very, very commonly used function, people write these functions, string compare, in the assembly. And as you learn from the assembly lectures, assembly is machine dependent. Even you are using the x86, according to your x86 version, according to what instruction set you are using, x86 even has several extensions. Based on this extension, there are multiple implementation for the str compare. So you can use more advanced hardware feature to implement a more fast string compare. SSE2 is one of the hardware feature, and what it says is that it is the string compare for the SSE2. You don't have to know what does it mean exactly, but just for your information, I just want to tell you. So you can just think of it as this is just the string compare. It crashed at the string compare. And to debug this one, you can check the call stack. If you check the call stack, then you can see this string compare is called by the search customer by ID, and this one is called by the register customer, and this is called from your customer manager and the clients. And if you try to see the code where this problem occurs, you might see that the our program crashed at the customer manager 1.c, which contains this string compare. But do you believe that this code caused the bug? Actually not. This code is where the bug causes the segmentation fault. But it is definitely possible that your bug exists in the somewhere else, and then this only caused the crash, and the debugger only shows where crash happened, not where your bug exists. Actually, bug is here. In our implementation, it does the realloc, and it put it to the P array for expanding your array. Do you see why is it the bug? Is there anyone who can guess why is it bug? Oh, sorry. Yes. This P array, as you can see from here, it is array of the structure user info. Realloc, the argument of the realloc is the size of the memory that you allocate in bytes. So what you need is when you allocate a memory for the struct user info pointer, you have to multiply the size of element. Here, the element is a struct user info to get the valid memory address. Otherwise, that it can cause the heap overflow. If you try to use this one with the index less than size of this new array size, so that cause the problem. So how can we detect this bug in a more convenient way? If you use GDB, you can find it, but you require to understand why this crash happens in a step-by-step, and then you need to run it step execution and try to do some other experiment with the printf. You can find those. But if you use address sanitizer, you can find this bug in a very convenient way. Let me show you. To use the address sanitizer, the first one you need to do is that you need to build a program with a special compiler flag, which is -f sanitize equal address. What it does is that it modify your program to use a shadow memory. We will explain what is a shadow memory, and then we make our program modify to check whether there is a memory error or not. This is a technique what we call the instrumentation. So this sanitizer, what sanitizer first does is that it instruments your program to change its behavior to detect a memory error. And then after you compile your program with the address sanitizer, and the next job is that just run the program to trigger the error. We know that our bug was triggered if we give a program with the -P2000. What you need to do is that just run this program with the -P2000, then it is done. Then what your address sanitizer will give you is that address sanitizer gives you this message. So instead of just crash with the with the segmentation fault, it gives more detailed information to detect the error. If you run this program with -P2000, it crashes and it gives such error. It says, address sanitizer says, heap overflow happens. On the address here, this is the buffer address that caused this overflow. And PC is a program counter, and it also shows you the stack pointer. BP is the base pointer for your stack, and the SP is the stack pointer that you get. And then you can see that what types of the buffer overflow happen. It says that the read of size 8. So what it says is that your program goes beyond its boundary, allowed boundary, by reading the size 8 byte. That's what this message says, and it shows the call stack of where this read happens. So this is call stack for this read, and what it also tells you is that where you allocate a memory. So this memory, which is the memory that caused the overflow, address sanitizer tells you that you allocate that memory here. This is what this address sanitizer gives you. So in terms of the heap overflow in most of cases, it is caused by the two reasons. The first one is that you allocate memory as you intended, but you mistakenly read this one over the boundary that it allowed. And second case is that you believe that you allocated enough memory, but it was wrong, and you try to read you try to access the memory beyond its size. So that's the reason why it shows you two types of the call stack, where you allocate it and where you use it. And if you go to the code that where you allocate memory, you will see this code. As we see before, this is where our bug happened. We missed the multiplication by the size of the element. So this is the root cause of our bug. And by checking this code, you can see this is customer manager 1.c line 137. So if we go to this 137, we can easily find it. So by getting this information, we can easily find this type of memory error. And just to briefly, if I explain this, how address sanitizer works in a very brief manner, what address sanitizer does is that it uses the shadow memory and the red zone. So what it does is that when we allocate a memory, it puts what we call the red zone. This red zone contains some metadata information for representing what types of the bug that can happen in this red zone. And then if your memory tries to access the memory, access a process memory, it also checks this shadow memory, and it checks whether your shadow memory is not touching, does not touch the red zone. If it touches red zone, it means that you did something wrong, and it catches it and it gives the error message. That's what this program does. Address sanitizer does. So what address sanitizer does is that by using instrumentation, it changes the code like this. So if you have this is the memory write, it changes this memory write. It keeps this memory write, but it adds an additional check. So what instrumentation does is that it does not modify the original functionality, but it adds some additional functionality without changing the original one. So if we do the read or write. In other words, if we do some pointer to reference, it puts this check. It checks whether this P touched the poison memory, is poison. In other words, it checks whether it touches the region. If it touches the region, it crashes your program and it gives some detailed information about error. Otherwise, it works as intended. So in more detail, what it does is that it's poison. What is poison does is that it checks when we access some memory. This memory has the region. So this is the memory that we cannot access. This is a memory that we are fine to access. And what is poison does is that it checks this pointer and checks its shadow memory and checks whether you touch the red zone or not. So this is the error message that we can get when we launch the address sanitizer. So if we do the address sanitizer, it shows this type of errors. And this error contains how your shadow memory looks like. 00 means that this is the memory that you can access. And this red means this is a region. And there are multiple types of region. One is FA. What FA means that it is heap left region. Heap left region means that this is the region that is allocated adjacent to your original memory. So this is the region that allows you to check the overflow. So by checking this kind of multiple types of the region, it can detect whether this is the heap overflow, stack overflow, or the use after free, or the shadow, the double free. Those kinds of things can be detected by this address sanitizer. So these are the memory errors that address sanitizer can detect. The first one is overflow. So what overflow means that we touch some address beyond the allowed memory region. So this is the example of the heap overflow. Here, we allocate a memory with the 16, and then we do the loop with the 16, and we initialize it with 0. Why does it cause the overflow? Yeah, so it has the same type of error that we discussed before. Previously, as we see before, when we allocate some array, then we need to multiply it with the size of the element. So here we are allocating into array, so we need to put the size of int when we allocate the memory, but we miss that, so it causes the overflow. And another type of error is the double free. We allocate a memory and free 2 times. This is what we call double free. And another type of debug is use after free, or we call it as a dangling pointer access in our lecture, in our EE209 lecture. We allocate a memory and we freed it. After freed, we access that memory, then it is what we call this type of bug. We call it as a use after free. And another type of the bug is a memory leak. So we allocate a memory, but we miss the freed, then it caused the memory leak. And address sanitizer can detect those type of the errors. And we will see how we can use the address sanitizer to detect this error. Let me show you with the my terminal. Here is the terminal. Let me show you how we can use the address sanitizer to detect multiple types of the errors. Hello, Manu, do you have any question? Or did you unmute by mistake? Yeah, I believe it was mistake. Okay, so I copied the code in the slide, so you can just copy the code and do what I'm doing now. And later you can repeat it if you want. So I copied all the code, and then let me compile this code. GCC minus O table, table.c, then it can compile without any compiler. Let me show you what this code does. So this is, I believe that this is the code. You are familiar with this type of code if you are taking the EE209. For someone who are not taking the EE209, let me explain it briefly. So we have buckets. So what it tries to do is that it creates a table using the array. That's what it tries to do. Sorry, we are here. What it tries to do is that it creates a table with the hash table. And we are using a collision resolution mechanism called the separate chaining to resolve the collision. You know, the collision is the when we do the hash table, when we make a hash table, we use a hash of key we use the hash of a key as an index to access the array. If two hash value of the different key are same, could be same because of the limited domain of the array. So if limited the output space of the hash, it could have the same value. In that case, we are using a linked list to resolve the collision. This is the basic implementation of the hash table. This is the hash function. And we create a table with the calloc, and our structure is the contains a single array with a fixed size. And when we do the table add, we allocate a memory and we compute the hash of the key, and we add our key and our values and the next, and we copy our key to preserve the ownership of this key. And then we put this node that we just created to the hash table. And what table search does is that it goes into the for loop and it checks it transverses the linked list and check whether key is equal to the given. It checks whether key is equal to the some node's key. If it is the case, it sets the value and the return 1, otherwise it returns 0. And there is a remove function. What remove function does is that it removes the node by this key. So similarly, it goes into the for loop and it checks whether the key is equal to the it checks whether key is equal to the some node's key. If it is the case, it updates the linked list and free them. And there is another function called the table free. What table free does is that it free all the elements in the linked list. It also free the array and the T. And this is our code for the testing. So we create a table and we add the 3 elements and we check whether Gary exists with the table search, and we remove it and we check whether Gary is existed or not. So what we expect is that if we run this with the first table search, we believe that our table will find this Gary because we just added, and we believe that the value should be 4. And after table removed, we expect that this will not be found, and our found value, which is return value of the second table search, should be 0. That's what we expect. Do you have any question about this code? Okay, good. So if I run this program, unfortunately, my program is crashed. So let's see why. Let's try to debug this code. But in this code, what you can see is that it crashes after the second table search. So after second table search, our program crashed. Then do you believe that there was no bug until the second table search? Actually not. Our address sanitizer can detect errors even though your program does not cause any crash, it can show you the error. So even though you have a memory error, not all memory error cause the crash. It is possible that it caused the bugs, but because your memory corruption by this memory error was not serious, so your program just worked as intended. But it does not mean that your program does not have any memory error. It can have memory error before your program crashed. So if we run this program, you will see these errors. It says that heap overflow happens. And it says write of size 5. We try to write 5 bytes over this allowed memory. And it happens with this table add. And this memory was allocated in here. So as I told you, overflow can happen in 2 reasons. We try to access in a wrong way, or we allocated a small address that we expected than that the program needed. So first, let's check whether our the copy code. Let's check where we write a memory. This string copy seems okay, right? We try to copy the key to our nodes key. So this copy seems okay. And let's check where we allocate the memory. Where we allocate the memory is line 34, this memory. Do you see any bug in this memory allocation? Do you see why it caused the overflow? Yeah. So when we copy the string, you always need to remember that we require 1 more byte for the null. But here we did not put we do not have enough space to store the null. So that's why it caused the errors. So to fix this error, to avoid this error, we should put the +1. We need 1 more byte to allocate a P key. Okay, good. So we fix the first bug and run it. But this program, our address sanitizer claims we have another bug, which is heap use after free. So let's see why does it happen. So we try to read a memory that is already freed, and free happens in this line. So let's check those. Oh, sorry. Line 95, it says we are trying to use the dangling pointer. In other words, we are using the P even after the even after we free. You can easily see why it is buggy. I think we have discussed in the lecture that the order of the free is very important. When we try to free something, we should remember that we cannot use that memory after the free. So here, the developer's intention is that it tries to free both key and the P itself, but it needs to keep the right order. So what it needs to do is that it needs to free the key first and then need to free P. Otherwise, we can use the dangling pointer. In other words, we can cause the use after free bug. So we need to keep the right order. Okay. Okay, good. So we found another bug. And then if we run this program, it says, oh, you are attempting the double free, which means we are freeing the pointer 2 times. So let's see why it claims that. So let's go to this 74, line 74. Oh, sorry. Oops. Line 74. And this is the second free. And it says our first free happens in the line 73. So this is the first free and this is the second free. Why it claims that we are doing the double free, even though we free the T array and the T? Is there anyone can see the why it happens? The hint is the data structure definition of the table. Do you see why it caused the double free? So when we do the free, we should do the free on the return value of the memory dynamic memory allocation function. For example, malloc or calloc. Here, T array is not the return address of the malloc. This is the element inside of this table. Right? And T array, as we learned in the previous lecture, in EE209, T array is just an address that points to the start of this array element. In here, table only contains one element, which is the array. So T array and the T points to the same address. So that's the reason why address sanitizer thinks you free the same memory twice, because T array and T points to the same address. So here what we need is that we should not free the T array. T array is the element of the T, so it will be freed if we try to free the T. So we should remove this line. Okay. Okay, good. So finally, our program works, but it says our program contains the memory leak. It's a leak sanitizer tells us we allocate those memories, but it was leaked. So let's see what are those memories and see why it was leaked. Here it says P key is the memory that was leaked is a P key. So P key is allocated, but there is no free related to the P key. So to understand that, we need to check where it should be freed. There are two positions that this one needs to be freed. The first one is that for the table remove. In table remove, we free the node, we need to free the key. Here, it seems good. It free our key, so it should not be the root cause of this memory leak. And the next place that it needs to free the memory is that the table free function. In table free function, you can see why memory leak happens. You can see we freed only the node, but not its key. So we should fit the P key before we free the node itself. Okay. So after we fix this memory leak, if you run this program, your program runs without any memory error. So that's the power of the address sanitizer that helps you to detect the memory errors. Okay. One thing I want to mention is that the address sanitizer is a dynamic analysis tool. What it means is that it can only catch the bugs if they are triggered. For example, let's assume our code looks like this. We allocate a buffer. Here is a buffer, and then we get the here is an int d, and we get the d from the user, and we set buff d equal to 0. Definitely, this code contains the overflow. If we give a d, which is if d becomes greater or equal to the 10, it will cause the memory errors. But even though we compile our program with the address sanitizer, let's assume that program is test. And if we give a number that does not cause the overflow, for example, if we give 1, even though this program contains the buff overflow, but address sanitizer cannot catch the bug, because address sanitizer is dynamic analysis tool, so it can only detect bugs if they are triggered. So to detect error, you should give some correct input that triggers the bug. For example, if you give the 10, then address sanitizer says that the stack buffer flow happens. This shows the limitation of the address sanitizer as a dynamic analysis tool. So it cannot catch all the potential error if you cannot trigger those. And the address sanitizer have the several pros and cons. Address sanitizer, the good thing about the address sanitizer compared to the other memory detecting rule, for example, the Valgrind. The one good thing is that it can also detect non-heap bugs. For example, it can detect the stack overflow and the global variable overflow. Those types of the bugs can be detected by the address sanitizer, but not Valgrind. And second one is that the address sanitizer is much faster. That's actually the main reason why nowadays address sanitizer is more popular than the Valgrind. Address sanitizer's performance overhead is only 2 times. So if you apply the address sanitizer, then your program will be slower by 2 times. So this is okay even with a very large program. For example, if you run the program browser, for example, if you want to apply the memory error analysis tool, address sanitizer is okay, but if you apply the Valgrind, this is too slow. It takes the Valgrind's overhead is on average it is 20 times. So if you want to apply this tool to the very large program, for example, browser, then Valgrind it is possible that it is not a valid option. And another good one is that the address sanitizer basically it supports the multi-threaded programs. So if you have a large program with a multi-threaded program, then the address sanitizer can help you to detect the memory errors. But address sanitizer also has some disadvantages. The first one is that you need to recompile your code. In other words, source code is required. But Valgrind is a tool that can work with a binary-only program. If you only has the binary, then Valgrind will work, but address sanitizer will not. So Valgrind can detect the memory errors in the compiled library. So if you only have the compiled binaries, Valgrind will work, but address sanitizer will not. And another one is that it cannot detect uninitialized memory. Valgrind can detect the uninitialized memory, but address sanitizer cannot. But one thing I want to mention is that there is another sanitizer type of sanitizer called a memory sanitizer. Memory sanitizer is more powerful than the address sanitizer, but it is more slower than that. Clang supports this memory sanitizer, and this memory sanitizer can detect the uninitialized memory like Valgrind. But address sanitizer itself does not support the uninitialized memory. So if you have any error related to the uninitialized memory, address sanitizer cannot detect that. Okay, this is the end of today's lecture. So the assignment for lecture 8 is that the deadline is same as before, and what you need to do is that you need to follow the same instruction in this lecture with the table C, and to fix all the bugs in table C and to submit the file to the KLMS. No screenshot or the JPG file is allowed, and to name the file as your student ID, not insert.c, sorry, this is typo, table.c, and upload the file to the KLMS. Okay. Do you have any question? No? Okay, good. Then we can stop here. See you in the next weeks. Bye-bye. Have a nice day.